All right, here we are. Last lecture of the week here, and we're talking about the most special molecule on the planet, which is water, because we have no life without it. And it has some really incredible properties. And we're going to go through those here together. So we're going to be talking about water in its different states: liquid, solid, gas. Water as a great solvent, and also what a solute is. How water has a high heat capacity. It's less dense when frozen, which is a very peculiar property for a molecule. And what acids and bases are, and what any of that means, and how that works. Okay, so liquid, solid, gas. Like where we left off, we were talking about salt, and we were actually talking about water. Very beginning today, we were talking about liquid, solids, and gases over here. So let's just, for water, it's pretty straightforward. Liquid, we just think of that as liquid water. So liquid water. The solid form, solid, we think of that as ice. It's called ice, right? And actually we should probably do that this way, because it would be solid, and then it would be liquid. And then it would be its gas form, which we call a couple of different things. So then in gas form, it would be water vapor or steam. And with the ice, so we'll kind of draw, our solid ice cube like this. And we'll talk a little bit about this, but if we kind of look at just the water molecules and the hydrogen bonds, remember that we have this six-sidedness to them. Oh, excuse me. So they look something like this. Not the best. And so I'll draw just another one here. But that's kind of the density of the water molecules. And in between this, they would have our little hydrogen bonds. That's kind of the density there of our water molecules in our solid form. And remember, they form this six-sided, beautiful crystal lattice of water. So this crystal lattice of water. They arrange themselves in a defined repeating pattern. That is a crystal. Liquid water, on the other hand, we got our little container, and we've got our liquid water, and then we've got our water molecules, which are densely kind of packed in here. So they're very closely associated with each other. And they're very moving, they're jostling around, they're all over the place. Like so. So we have our densely packed, density, if you don't know what that means, it means how close something is to each other. So you could have 10 people in a room that are all crammed in the middle, or you can have 10 people in a room that are all spread out. So something that's very dense is all crammed together. Something that is diffuse or not very dense is all spread out. Densely packed water molecules. And remember, water is a compound as well as a molecule. Densely packed water molecules in liquid form. And they're all bouncing around. Here they're all stable. They're not moving very much. They're wiggling a little bit in their positions, but they're not really moving. All right, and then in our gas form, you can basically kind of just redraw this. But again, we've got our water, got our densely packed water. And some of these are starting to wiggle out and get up into the air. And that's because maybe we're applying some energy to this to cause them to wiggle more. All right, so then this would be our gas, water, vapor, oops, slash gas, slash steam. This is what we call this. It takes a lot of energy. So these water molecules are sticky. They're stuck to each other, remember, because of those hydrogen bonds. We'll keep coming back to this, but those are the basic 3 states of water. And you can play with all these in your damn kitchen. You can go into your freezer. We didn't always have freezers as human beings. Like, that's a special kind of cool thing that we have. Get it? You could go take an ice cube, you could put it in a pan, you could heat it up, and you could watch it go from these 3 states. That water will disappear if you put it on the stove. Even if you just take an ice cube and you just leave it on your counter, that thing will disappear. Where's it going? It's going into the air. It's diffusing away into the air. It's going from a liquid to from a solid to a liquid to a gas. Sometimes, actually, like if you pull an ice cube out of the freezer and look at it, you'll see some steam coming off of it. And that's because some of the water molecules can go right into the gas form. So some of them will just leave this ice cube. That's called a little fancy thing. Don't expect you guys to know this, but it's called sublimation. That's when a solid goes directly into a gas. To a gas. Sublimate. So you could have an ice cube in the freezer, and eventually that thing will just disappear because it'll kind of become a gas. It will sublimate. Pretty cool. Okay, solvent versus solute. All right. Well, let's bring our friends back. Let's just look at these. How do I want to do this? I kind of drew these crappy because they're the same color. Well, let's redraw them. We'll redraw the water molecules. So I'm going to bring these back. These are our sodiums and our chlorines. And we'll put those over there. So we talked about liquid, solid, gas. We'll check that off. Solvent, solute. Let's talk about that. What is a solvent? Solvent. It's something you use to clean the floors. Solvent is a liquid that dissolves things. That's what it is. That's what a solvent is. A solute. Solute. Kind of sounds like salt. Solute. Salt. Solute. It is what is dissolved. All right. Water. H to the ISO. Water is a fantastic solvent. Remember the special little properties of water? What were those? These little special properties. Let's bring these back. Let's bring this back up here. You don't have to redraw this whole thing. I just kind of want to have it up here so you can see it. It's a fantastic solvent. So it has this partial charge. Water has a partial charge. So the oxygen is partially negative. Negative. Put that in red. We'll highlight there. Actually, I have a highlighter. Look at that. Partially negative. The hydrogens are partially positive. Positive, we do it blue. Right? So, anything that is charged is going to dissolve well in water. Anything that dissolves well in water, this is a little definition. Anything that dissolves well in water, it's called it likes water, or this would be polar. Another word for this is polar molecules. Well, that's not quite accurate. Polar molecules will dissolve well in water, but anything that has a charge is a polar molecule. Let me get rid of that. Anything that is charged is a polar molecule. So water is a semi-polar molecule. This is a polar molecule. It's going to dissolve well in water. Anything that likes water, anything that likes water is called hydrophilic. This means water. Hydro, that means water. And philic means loving. Okay, so we'll talk about specifics of this, but let's just continue on this little train of thought. Anything that dislikes water, doesn't want to mix with it, it's called hydrophobic. So again, this means water. So hydro means water. And phobic means fearing. Water fearing. Okay, so one example of this would be salt. Salt loves water. You can do this experiment in your kitchen. You can take salt and you can see it dissolve in water. If you cook, you do this all the time. Anything that dislikes water is called hydrophobic. An example of this would be fats. You can take oil. You can do this again in your kitchen as well. You can take oil and you could try to mix it with water and see what happens. The oil will kind of stay on the top. And that's because fat is non-polar. It doesn't have a charge. It's not charged. Not all molecules have a charge like this semi-charged state. It's non-polar. It's not charged. It has no magnet-like properties like water does. So it doesn't like to mix. Okay, so water is a fantastic solvent for anything that's charged. Well, this, I don't know if you remember what these were. These were chlorines, CO, which had a negative charge. And then these were sodiums, right? Which had a positive charge. So this is why sodium or water loves salt, and why salt dissolves in water. So what happens if you were to put this in water, these molecules would start to break up. So this would start to come off, this would start to come off, this would start to come off, this would start to come off. Let's just do those four. So now these are suspended by liquid water. We'll draw our waters now. We'll just draw them all in blue. We'll just draw them quick. We'll just draw two around each one of these. Like so. And we'll draw our little hydrogens as little black ears on these. So this is negative, so that means the hydrogens are actually going to want to interact with it, because the hydrogens are the positive part. These are positive, meaning the oxygens are going to want to interact with it. So we'll draw our hydrogens like so. Okay, and there's going to be some attraction here. There's not going to be any real bond, but there's going to be some attraction because this is partially negative and partially positive. So these water molecules are going to surround these ions, and they're going to bring them into liquid water. Pretty cool. So there's going to be, of course, a bunch of other water molecules out here. And now it basically takes this solid and dissolves it up into the solution. And the reason why they like each other is because of these charges, right? Because this is going to, over here, let me just draw in these charges. This is going to be negative, a negative charge, right? These over here are going to be slightly positive, but I'm just going to draw them as positives, so they will interact with each other, right? You see how that works. Whereas this is going to be slightly negative here. You can't really see that great. Redraw that in maybe a lighter gray. Yeah, like that, much better. And this is going to be positive. This is going to be negative. Okay, and there would be more water molecules surrounding these. I just kind of drew it simply like this. All right, so that's why water is a great solvent for polar things. It will easily dissolve them. This is also, interestingly, why if you take salt and you mix it with ice, this is why we reduce we increase or decrease the I have to think about this for a minute. Water will be in liquid form at lower temperatures if you add salt, because salt and water will enter into this state. It will actually, the salt molecules will actually pull the water molecules out of the liquid state. I have a little diagram of this. I don't want to draw this all out just to kind of save time here. So it lowers the freezing point. So we have this salt. Oh, this is the dissolving of salt and water. This is not actually salt pulling water out of a crystal. This is what I just drew, actually. But that's cool. You can see it again here. Dissolving of salt and water. But if you then had these crystal forms of water, salt will actually pull it out of its solid form, and they will both then enter into a liquid form. And so even at 32 degrees Fahrenheit or 0 degrees Celsius, those are the same, you will have liquid water. So if you ever want to super chill something very quickly, you can add a little bit of salt to ice, and then you will have super cooled water, because it will still be at that lower temperature, but now it will be liquid. Normally it would be frozen solid, but now it's liquid, and so it can bind to the surface area of, like, let's say a can of Coke and super chill it faster than if you were to just put ice around it, because you have more contact with the can of Coke, but you have super cooled water. Okay, solvent, solute. Okay. Beautiful. High heat capacity. All right, let's go to this liquid water molecule diagram here. And let's bring this bad boy back. What does heat capacity mean? Water has a high heat capacity. What does that mean? Water has a high heat capacity. Well, if you've ever boiled water, you know what I'm talking about. It takes a long time to boil it. It takes a lot of energy. I mean, think about that. You make a pan, you fill that water, and then you burn it with fire, and it takes minutes, depending on how much water you have in there, for that to then start to becoming gas. Like, you have to dump in so much energy into water to turn it into a gas. And that's because, look at this. One of these water molecules is bound to 4 other liquid water molecules. So these hydrogen bonds are what give water its high heat capacity. Has a high heat capacity. Each water molecule is potentially bound to 4 others through hydrogen bonds. That's pretty crazy. You can think of these as rubber bands between each molecule. And so if you want to separate them, you got to put in a lot of energy to bang those water molecules into each other. Heat is just how wiggly something's atoms are. That's what heat is. How wiggly is something's atoms? So if you want to disconnect these, you have to add enough energy to get them going, to build enough motion within them to then say to this water molecule, I'm done with you guys. Boom, I'm out of here. Whee, gone. Now I'm a gas. I'm floating around in the air. I'm having a good time. It takes a lot of energy to do that. A lot of energy to do that. It's in fact, it takes, that's how we define a calorie. The amount of energy needed to change the temp of liquid water, why can't I not spell liquid? Liquid water, 1 degree Celsius is, and it's a certain amount of water, I think it's 1 milliliter, doesn't matter, is how we define a calorie. That's how we define a calorie, is by that. And it takes 1 calorie to change 1 mil of water 1 degree Celsius. And that's actually a small calorie, not the kilocalories that we talk about when we talk about food. Okay? So when you add fire to a container like this, I'll just redraw that because that one's not even very good. All right, I'll just redraw that. So when we got our container, we got our fire, we got our liquid water, and we got our water molecules all in here, and they're all bouncing around, moving around, having a good time. It's a stellar time. They love it. So this is going to stay liquid until it gets to, so this will stay liquid until it boils. And what is boiling? Well, that's when now there's enough energy. And we'll just recopy this, paste it over here. Boiling is now there is enough energy to break, we'll say disrupt the hydrogen bonds. Okay? And so now what's going to happen when that happens, when this is boiling, now the water is going to start to be converted into vapor. Water will be converted to gas / steam / vapor. Crazy. Okay? And now all of the energy that you're dumping in, so from here to here, I don't want that to be so thick, there will be a rise in temp until you get to 100 degrees C. And then the water will just stay that temperature. It'll just stay 100 degrees C. And then all of the future energy that you're still pumping a bunch of energy into it. It will then go into breaking those hydrogen bonds and converting that liquid into a gas. That's where that energy's going. It's kind of a weird thing. You probably don't ever really think about that, but the water will always be 100 degrees C unless you were to really crank up that heat. So we said it takes, where did I write that? It takes 1 degree C. If you want to change, it takes 1 calorie. If you want to increase the temp of water from 100C from 100C to 101C. This should only take 1 calorie, right? This should, because this is only 1 calorie right here to change it 1 degree. But we're talking about this boiling point where water is being converted. So now if you want to do it here, if you want to increase the temperature of water here, this is crazy. Now it takes, this would take 540 calories. You have to dump in so much energy so quickly to be able to make that change. This would take 504. Oh, this, sorry. My number pad is not working. Calories. Because all of the energy wants to go into this process. It takes energy to convert these little elastic bonds. Those would rather break and the water would rather go away than have it stay into this form. Okay, and the exact opposite is true. So now let's say we got this water vapor over here. This is steam, right? And then we've got some poor schmuck's hand. Maybe it's me. Oh yeah, I got a claw hand. Okay, that's trash. All right. Tori's hand. Tori's claw hand. All right. And now this gas vapor, this steam, now has a bunch of energy in it, right? And now it's going to go back into this liquid form. And so now it's going to accumulate on my finger and become a liquid again. I'm getting a little excited here. Becomes a liquid again. Ouch! It's going to dump. It needs to release energy to do that. That energy has to go somewhere. It's got all this energy. Where does it go? It goes into my finger. The energy released from converting from a gas to a liquid goes into my hand. All right. Ah, and then that hurts. Ow. Way more than if I were to just, for the same amount of time, if I was to just dip my finger in that boiling water, it would hurt. It would cause more damage to be burned by steam because all of that energy that's within those water molecules needs to be released in order for them to settle down and become water again. And it has to dump that into its environment, which is my hand. In other words, steam burns are worse than hot water burns. Because the energy needed to convert a gas to a liquid again, that requires an energy loss to occur, and all that energy has to go into your finger. Okay, so that's high heat capacity water. Very special property. Little sticky Mickey Mises. Why does it have a high capacity? Because water molecules are little sticky. Yeah, I think I like the T's. It makes it rhyme better. Little sticky Mickey Mises. And yeah, I'm not saying that right, but it's funny. Hate me. Okay, high heat capacity. Done. All right, less dense when frozen. This one will be quick. We've already talked quite a bit about this, but it's an important one. It's a really fascinating one. I'm just going to pull up a little image here. Right here. All right, so water is less dense. Water is less dense when frozen. We're almost done here, I promise. I know you hate me because I went real long this week, but chemistry's cool and we only got 1 week, and I was supposed to talk about organic molecules today too. All right, so we've got frozen water and we've got liquid water. You can just see how tightly packed these liquid water molecules are. When you freeze water, it forms this beautiful crystal lattice pattern, and the molecules actually are further apart now. And that's what we mean by less dense. And what this means is pretty cool. In a biological context, within the environment, I know this is human biology, but I think this stuff is freaking awesome. And also I could show you this picture of this otter here, which is dope. What this means is that frozen water floats. And you can test this in your kitchen too. Frozen water floats, which allows our lakes, our rivers, all that water, bodies of water that freeze, to have liquid water underneath it. If this wasn't true, these bodies would freeze solid through. So this water would freeze, it would sink down, and then that water would freeze, it would sink down, it would freeze, it would sink down. This would change life on Earth. So this property of water gives us these organisms. Like otters wouldn't be able to fish in the winter. They wouldn't be able to live in these climates. Turtles, frogs, they wouldn't be able to burrow down here. All of this would change. We'd have fish wouldn't exist in freshwater during the winter. They might still exist, but they might have to like enter dormant phases or something. Life as we know it would be different on this planet if it wasn't for this property of water and also this property of water. I didn't talk about this, but this is let me go back. This is important. This is why we sweat. This is why we cool ourselves by going swimming. When you sweat, the heat from your body goes into boiling off this liquid water. So this liquid water absorbs all of that heat from you and converts it into becoming a gas. Very important. This is why we sweat. This is why we sweat, to cool ourselves, because the water absorbs so much energy to be converted to a gas. Okay, sorry, I cannot believe I forgot that. It's so cool. This is why we like to go swimming, and this is why if you take rubbing alcohol, this is a good one, works similarly. It evaporates very quickly. And you will feel your skin cool very quickly there. So when things evaporate off your skin, you feel very cool because that energy from your skin has to go into that conversion process of converting something from a liquid to a gas. Okay. All right, I think that's all I wanted to talk about with the density of water. So now we just need to talk about acids and bases, which will not take long. And there's so much more I wish I could talk about here. I don't have enough time ever. Okay, acids and bases. All right, let's redraw a hydrogen atom. So acids and bases. What the heck is this crap? Let's redraw a hydrogen atom. Acids and bases. What is that? We'll talk about it. Acids and bases. All right, let's redraw a hydrogen atom. And we're going to draw it, so this is a hydrogen atom. Hydrogen atom. We're going to redraw it as a proton, right? Proton. Proton. And it's got its valence shell. And it's got an electron, right? And we got ourselves an electron. That's a hydrogen atom. Whoops. It's freaking easy. One proton, one electron. Okay. Acids and bases. What are these things? All right. Well, sometimes what happens when you have water, or hydrogen inside of the water, we'll just say, it's a little more complicated than that. We'll talk about it. This can happen. This electron can say, sayonara, bro. I'm over here now. Later. Okay, so now we got a proton, which is what? Positive. And we got an electron, which is what? Negative. So we got a proton and we got an electron. Well, guess what? This is an acid. This is a base. That's what that means. We're talking about protons and electrons. Really what happens is something like this. It's not quite as simple as this. We have, draw out how this actually works inside of water. It actually has to do with the water molecules. So we've got our water molecule. Whoops. We got our water. We got our hydrogens. Or that's our oxygen. These are our hydrogens. And we got another one, let's say. Boom. Okay. What can happen is this can go in actually either direction. So this can go in this direction. Oh boy, that's, you know what? Let me draw this like a man. There we go. Still, oh boy, what am I doing? Still not great. Ah! All right. Yeah, that's how men do it. All right. Okay, so what can happen? You add these together in chemistry. I'm doing like a little chemical formula here. So we add those together. Sometimes we can get this. We add these together. Sometimes we can get this. What happens is sometimes one of these flops over here. One of these protons goes over there. That's just the proton itself. So then over here we would have this water molecule would be positively charged, and this water molecule over here would be negatively charged. Right there. And this thing here is called a hydronium ion. That's what this thing is called. That's a proton or a hydronium ion. This would be a hydronium ion. Hydronium ion. H3 plus. Okay, so when we talk about acids or bases, we talk about something like pH. Oh, are you pH balanced? Oh, you can go get water that has a pH of 8.7, and oh, then you're not going to get cancer and all this hoity-toity. No, I don't know if any of that's freaking true. The idea behind that is like spring water and things like that have minerals in it. So are you getting more mineralized water? Probably better for you, but drinking exact pH water is probably total garbage because your body can regulate its own pH through buffers. Like your body is totally capable of doing that. Okay, so pH, what does that stand for? It stands for the power of hydronium. And so, power meaning it's times 10 every number. The pH scale goes from 0 to 14, and everything in between. And 0 to 14, and we have 7 right in the middle, obviously. So we have 7 right in the middle. All right, so these values over here are going to be acidic, and these values over here are going to be basic. So if you want to, burn your homie because they're being a little basic B, maybe they're, I don't know, listening to Drake, wearing Ugg boots, drinking a pumpkin spice latte, talking about TikTok. Like, that's some pretty basic B stuff right there. So you can be like, you got a pH 14 over there, dog. What is you, oven cleaner? So we'll talk about some various things that fall in here. Yeah, so oven cleaner kind of falls in right here, around 13 or so. Oven cleaner, it's around 13. Some other, what's some, bicarbonate, sodium bicarbonate, sodium bicarb. Sodium bicarbonate. That boy falls in around 12. That boy falls in around 12 right there. But ammonia is around 11. 11. Ammonia. I'll have to use that as a cleaner. Like the Great Salt Lake is around 10. 10 is the Great Salt Lake. Great Salt Lake in Utah. Boy, it's pretty basic. Pretty cool, actually. Baking soda, stomach antacids are around 9. What in the heck? What are you doing? Keep doing that. Keep making the same mistake now. All right. So this would be, no thank you. What is that? That is ugly as heck. Okay, this would be baking soda. Baking soda. Egg whites, and human blood are around 8 or so. Around that area, 7 point something, 8. So this would be like egg whites, human blood, and they're like a little bit less than 8. Okay, so now we're talking about more acidic things. What color do we want to do those in? We'll do those. I did these all in blue. That one should have been in blue, sorry. We'll do these all in this little pink color. So this would be pure water. Pure water. Like pure distilled water would be a pH of 7. This one's also good. Tears are a pH of 7. Okay, and then we'll work our way, let's keep working our way down. Interestingly, like in between 6, I think this one's pretty crazy. Like, not that crazy, I guess, but like right around here, we got milk. So it's a little slightly acidic. Normal rainwater, it's about 5. So this is normal rainwater. Pretty cool. It's pretty acidic. Normal rainwater. Guess I should do these like this. I don't really know how to do that. No, don't know I'm gonna have enough room. All right, we'll just keep going. All right, this one, wow. This one's also gets like a little bit less than that, kind of in between 4 and 5. We've got, so let's just kind of put this like right here. This is good. We got bread and coffee. Pretty acidic. All right, right around 4, we got tomatoes. All right, now we're getting into some pretty acidic stuff. Pretty acidic stuff right here. This one, soda. And that's because it's a lot of carbon dioxide in water. That makes an acid. And we'll talk about that. We'll investigate that. Beer, vinegar. Soda and beer are as acidic as vinegar. And that's because they're full of CO2 in water. And we'll talk about why that makes things acidic in the future. 2. And then we got 1. Something at 2 is like lemon juice. Like, think about that. Soda's about as acidic as lemon juice. Not quite, but almost. And that's why it's so bad for your teeth. All right, then at 1, we got stomach acid. Stomach acid. And then we have pure hydrochloric acid ranking in at 0. Pure hydrochloric. So this would just be pure HCl. Hydrochloric. There we go. Acid. All right. Pretty crazy. Don't drink soda. Don't drink beer. It's bad for you. It's a poison also. instead of drinking those, you might as well just drink some vinegar because it's the same freaking thing. Isn't that crazy? I think that's pretty crazy. Still surprises me to this day. It's only 2 steps above stomach acid. Why not just throw up in your own mouth instead of having a nice crisp Coca-Cola? All right, we will end it there. There's one thing we'll talk about, but basically buffers, pH buffers. We'll talk about these. pH buffers keep the pH stable. So if you have a buffer in a liquid and then you add a bunch of acid to it, it'll absorb that acid. It kind of acts like a paper towel or a sponge for pH changes for acids or bases. So it acts as a paper towel or sponge to absorb acids or bases. That's what a buffer is. Pretty nifty. Yeah, that was a lot that I just went over just now. That was probably another 40 minutes. I'm sorry, but you know, I technically get 3 hours of lecture every week with you guys. So as long as I'm under that, I'm doing okay. I try to do even less. So a lot in there. If you have questions about this stuff, this was a lot. I essentially gave you an entire course in very simple chemistry and water chemistry in a week's worth of lectures. I wish I had more time to spend on all this because I find it extremely fascinating. Lot to talk about here. And I had to kind of go over some things quickly. So please let me know if you have questions about this stuff. Feel free to ask them in lab or shoot me a message. All right, I'll see you guys in the discussion post and in lab next week or in this week here coming up. All right, bye.